Chapter 15 will be over acids, bases, and salts. So let's go ahead and start by talking a little bit about the definition of an acid. We will be talking about the Arrhenius definition of an acid, which means that Arrhenius acid is an acidic solution, so it's an aqueous solution of an acid. It has to be dissolved in water, and when it dissolves in water, it produces an excess of H plus ion, hydrogen ion. So common properties of acids is that it tastes sour, it turns litmus paper to pink or red color, and it reacts with metals to produce hydrogen gas, reacts with bases to produce water and a salt, reacts with carbonates to give carbon dioxide. On the other hand, we want to talk about the definition of an Arrhenius base. Arrhenius base is a basic solution contains an excess of hydroxide ions. So again, it's the same thing. Anything that's a basic solution, this is a base dissolved in water, aqueous solution, and then when it's dissolved in water, it produces hydroxide ions. Common properties of bases. So let's go ahead and fix that. This is for base. They taste bitter. They turn litmus paper blue. They feel slippery or soapy, and it can neutralize acid. So ammonia right there is an example of a base. Acids can react with metals and bases. So let's talk about acid reacting with metals. When an acid reacts with metal, it will always produce hydrogen gas. So what type of metal can react with acid? It has to be a metal that stays above hydrogen in the reactivity series. In general, acid plus metal equals to salt plus hydrogen gas. So on the other hand, acid can react with base. This is called a neutralization reaction, where you have an acid reacting with a base, you make a salt and water. So in general, acid plus base equals to salt plus water. Next, we can talk about the reactivity of metal oxides with acids. So if you have an acid plus a metal oxide that is considered a base, it can produce salt and water as well. Next, let's talk about reacting an acid with metal carbonate. So this is an example of a metal carbonate, just a metal ion and a carbonate paired together to have a carbonate compound. So acid plus metal carbonate will give you salt, water, and carbon dioxide. So carbonate will yield carbon dioxide. So we mentioned some of the reactions produces salt. So what are salts? Salts are products from acid-base reactions after you do the double displacement. So H and OH makes the water, and an Na and Cl will make the salt right there. Salts are ionic compounds. They contain a cation, a metal cation, or an ammonium ion derived from the base, and an anion derived from the acid. So you have the cation from the base and the anion from the acid. And all together, you make a salt, which is an ionic compound. In general, salts are crystalline compounds with high melting and boiling points. So let's practice. Which salt forms in the reaction of aluminum oxide and hydrobromic acid? So again, you have an acid reacting with a metal oxide, you will make salt and water. So if you have acid with oxide, metal oxide, you will make your salt, which is Al and Br combined together, and H will form with O to make water. So in this case, Al and Br will pair as AlBr3 because aluminum is 3 plus charge, bromide is -1 charge, so you need 3 of the bromides to pair with 1 aluminum, so you need to have AlBr3. So our answer will be B. Electrolytes are compounds that conduct electricity when you dissolve it in water. The reason why it conducts electricity when you dissolve it in water is because as it dissolves in water, it forms ions, and with the formation of ions, you have electrons being released or received. So with the presence of electrons flowing, you can conduct electricity. Now, non-electrolytes, on the other hand, are substances that do not conduct electricity because when they dissolve in water, they do not form any ions whatsoever. So let's compare some solution conductivity. Let's use water as our control. Pure water with no ions in it should not have any conductivity. Now, if you use sugar solution, you pour some sugar and dissolve it into the pure water, it will also not light up the light bulb because it doesn't conduct electricity, so this is a non-electrolyte. On the other hand, if you use salt solution, which is an ionic compound, you will be conducting electricity because the ions are forming as you dissolve the ionic compound in water. So this will be considered an electrolyte. So let's go over some examples of electrolytes. So again, remember, electrolytes conduct electricity because of ions. And ion movement or electron movements here causes electricity to be conducted in water. So there are three classes of compounds here. Acids, bases, and salts are considered electrolytes because they produce ions in water when they dissolve. Definition of an acid is where when you dissolve in water you have an H. So you have an H plus in your compound somewhere. Okay, so let's look for acids in our list here. See, this is H plus and an anion, H plus with an anion, H plus with an anion, H plus with another anion. So these are called polyatomic ions. So you do have to memorize your polyatomic ions. But anytime you have an H plus with an anion, these are considered acids here. Okay. Now, if you have bases, bases are defined as something that dissolves after you put it in water, dissolve in water, it will produce hydroxide ions. So you must have a hydroxide ion in your formula. So you must have a hydroxide ion paired with a metal cation or hydroxide ion paired with ammonium cation. So it's usually metals and ammonium hydroxides. This one is just hydrogen ion plus an anion. On the other hand, salts are cations and anions paired together, so there's a lot more options for salts available. So this is a base, that's another base. These guys 1, 2, 3, 4 are acid, and these are two examples of salts here. And on the other hand, non-electrolytes are things that cannot form ions when you dissolve it in water. Okay, so don't mistake these hydroxide or OH groups here for bases because they are not paired with a metal cation or ammonium ion. It's just paired with C and H here. So these guys here are non-electrolyte. Okay, non-electrolytes also have no metals in them. It's just all non-metal stuff. So here's a question, which compound will not dissociate in water? That means when you put it in water, it dissolves in water, it does not split into ions. HCl will split into H plus and Cl minus. KBr, so that's an acid. KBr is going to split to K plus and Br minus, so that's a salt. So these two will split, acid, salt, and sodium hydroxide will split to sodium ion and hydroxide ion. This is a base. So the only one that does not dissociate in water is CH3OH because it's an OH, but it's not paired with a cation here. It's paired with C and H. So this makes it a non-electrolyte and it does not dissociate into ions when you have it in water. Salts dissociate into their cations and anions when dissolved in water. So if you have sodium chloride, it goes into sodium ion and chloride ion. So how does it actually look like when it's in water? Sodium will be flanked by the negative side of the water, which is O. And then Cl ion is negative charge, so it will be flanked by the positive side of the water, which is the H side. So that's the explanation of where the ions are attracted to which end of the water. The permanent dipoles in a water molecule cause specific alignment around the ions. That's because water is polar, so the polarity of water will always align with the opposite charge of the ion that it's around. So ionization is the process of ion formation in solution. Ionization results from the chemical reaction between a compound and water. So let's see. Acids ionize in water, producing hydronium ion, or hydronium ion is pretty much the same thing as H plus, and a counteranion. So if it's HCl plus water, you'll make hydrogen ion and Cl negative ion. You can also say if you didn't write water in here, it will just H become H plus, Cl will be Cl minus. Because you add the water in the equation, the H gets put onto the water and it becomes a hydronium ion. So another example of acid ionizing in water is H3PO4. This is phosphoric acid. You plus water, you make H2PO4 -1 and hydronium ion, because the H plus from this guy goes into this, so makes H3O positive. And then what's left over after you took a H plus out is H2PO4 -1. Bases ionize in water, producing the hydroxyl ion and the cation. So for example, ammonia is a base plus water. You'll make hydroxide ion because the water splits into H and OH. Okay, so hydroxide is left behind, and the H from the water will go onto this guy to make ammonium ion. So let's talk about strong and weak electrolytes. Strong electrolytes completely ionize in water. All of them turn into ions. So example is strong acid. Weak electrolytes are incomplete ionization because it goes back and forth. It's a reversible reaction. For example, acetic acid is a weak acid. So if you take a look at this picture here, HCl here, hydrochloric acid, is going to dissolve in water and it's all split into ion form. See, the Cl and H are all separated in the solution here. If you were to dissolve acetic acid, you would get mostly you have molecule forms. That's a molecule form, molecule form, molecule form, molecule form, molecule form, molecule form, and then that's a molecule, molecule. But then there's one ion, and there's another ion here. So this is the anion, the acetate ion, and the cation, the H plus. So most of it stays as a compound, but some of them, or very few of them, will actually ionize. So this is why acetic acid is a weak acid, and it's a weak electrolyte because they have less ions in the solution. So here are some examples of strong and weak electrolytes. Strong electrolytes are most soluble salts. So if you remember the solubility rules, all the salts that are soluble in water will be strong electrolyte. Strong acids are also going to be strong electrolytes. So H2SO4 is strong acid, that's sulfuric acid. Nitric acid is also a strong acid. Hydrochloric acid is a strong acid. Hydrobromic acid is a strong acid. And then this is perchloric acid is also a strong acid. So these guys are considered strong electrolytes. And then when you look at bases, group 1 and group 2 hydroxides bases are strong electrolytes. Okay? Now we have weak electrolytes are weak acids. This is acetic acid, carbonic acid, nitrous acid, and all these leads a list of acids here that are weak. Okay, so most of the time, if it's a weak acid, it will just split partially and it'll have very few ions. So if you ever have a light bulb on it, it will be kind of pretty dim. It'll get lit up, but it's dim compared to these guys. This will be really bright. So here's another example of weak acid. And then you have a weak base example here, ammonia, and hydrofluoric acid is also a weak acid. So the double arrow indicates incomplete ionization because it goes back and forth. So these are typically also weak electrolytes. Okay, so anything that has reversible reaction where it goes back and forth, because they can't stay as ion form a lot, most of it stays as molecular form. So let's talk about salts. Salts will dissociate into the ions it came from to build it. But and sometimes it makes up more, is made of more than 2 ions. So that depends on the compound. So if you have 1 molarity of NaCl, it will produce 2 molarity of ions because 1 molarity of Na plus another molarity of Cl minus. So you end up getting 2 molarities of ions. Now if you have CaCl2 on the other hand, this one splits into 3 ions. One splits into 3. So if you have 1 molarity solution of CaCl2, you will produce a total of 3 molarity of ions because 1 from calcium and there's 2 moles molarity of chloride ions. But one good thing is the salts are complete dissociations. So dissociation of salts practice. What is the concentration of bromide ion in a 1.5 molarity solution of magnesium bromide? So 1 mole magnesium bromide will split into 1 magnesium and 2 bromides. Okay? So that means if they want you to look for the bromide ion solution, the bromide will always be double of magnesium and magnesium bromide. So if 1.5 molarity is magnesium bromide, the bromide will be double of it, so it will be 3. So let's talk a little bit about auto-ionization of water. It's pretty interesting. Pure water very rarely is 2 in a billion time. Out of a billion of them, 2 of them will convert. Self-ionizes into a reaction here where you have water plus water equals to hydronium ion plus hydroxide ion. So basically one of them splits, the H goes to the water, so you get H3O plus, and then what's left behind is OH. So based on that, we also know that H plus or hydronium ion concentration is the same as hydroxide ion concentration, and this will be 1 times 10 to the minus 7 molarity for pure water. And that means that if you take H plus and OH minus, which is the same number, 1 times 10 to the minus 7, square that term, you get 1 times 10 to the minus 14. This term of H hydronium times hydroxide is called Kw. You will learn this more in later classes, but it just means that hydronium times hydroxide, or sometimes interchangeably I'll just call this hydrogen ion. It's the same thing. So that will give us 1 times 10 to the minus 14. Now, when an acid and base is present in water, the H and hydronium ion and hydroxide ion ratios will be a little different. If it's acidic, you have more hydronium ion than hydroxide ion. If it's a basic solution, you'll have more hydroxide ion compared to hydronium ion. So while we're talking about acids and bases, it's good to learn about pHs. The definition of pH, the formula is pH equals to minus log of concentration of hydronium ion. So in pure water, hydronium ion concentration is 1 times 10 to the minus 7. So pH is minus log of 1 times 10 to the minus 7. So my pH for pure water is 7. So 7 is the neutral point here, and that's the 10 to the minus 7 concentration here. If you want to make it more acidic, you have to increase the concentration of H+. And as you can see, every 1 unit of pH is 10 times in pH in hydronium ion concentration. Hydronium ion and hydrogen ion are interchangeable here, okay? And then on the other hand, base, it means that there's less and less, 10 times each time, less of hydrogen ion or hydronium ion. And that will give you a higher pH, and it's going to be more basic. At higher pH values, you'll have low hydronium ion and high hydroxide ions. At really, really acidic pH, which is low pH, you have a lot of hydronium ion and very little hydroxide ions. So some pH of common solutions, gastric juice is about pH 1 because we have some hydrochloric acid in there. Hydrochloric acid, 0.1 molarity is about pH 1. Lemon juice is acidic, so it's about 2.3. Vinegar is acetic acid, is about 2.8. Here's an acetic acid right here, 0.1 molarity, it's 2.9. So we see how it's similar to the vinegar you can buy in the store, and this is the actual formula of acetic acid, which is also vinegar. Orange juice is acidic, about 3.7. Tomato juice is about 4.1, still acidic. Coffee, black coffee is still acidic, 5.0. Urine is 6.0. So that's still considered acidic because it's not 7 yet. Milk is 6.6, still fairly acidic. Pure water at 25 degrees will be considered 7. Okay, now blood has household ammonia and sodium hydroxide. These are going to be basic pH values here. So we talked about a pH scale. We said each time the pH changed by one number, it's 10 times in a change of hydrogen ion or hydronium ion concentration. By what factor of a solution that has pH 3 is more acidic than a solution of pH 5? So because it's 10 times each number for pH, 3 to 4 to 5, it's actually twice that you two numbers up. So it'll be 10 and then 10, it'll be 10 squared. The answer will be 100 times more acidic. And if you take a look at the formula, you have you can see here hydrogen ion here, or hydronium ion, when pH 5 is 1 times 10 to the minus 5. When it's pH 3, you have 1 times 10 to the minus 3. And obviously the difference here is 100 times. pH 3 has 100 times more hydronium ion than pH 5. So let's try some pH calculations. 0.015 molarity of hydronium ion solution. So the formula of pH is minus log of hydronium ion. So minus log of 0.015 will give us the answer of pH. If you do this on your calculator, you should get 1.8. What is the pH of 0.02 molarity HCl solution? So here's the molarity. pH is minus log of H. So that would look like this. Minus log of 0.02. And that should give us, when you do your calculation, you get 1.7. So our answer is D here. So next thing is, if you have a hydroxide that you need to calculate the pH of, here is an interesting thing that I haven't shown you. So you need to know that pH, there's a complementary scale called pOH. And these two numbers add up to 14. Okay, so if you know pH formula was minus log of hydronium ion, or H plus, pOH formula is very similar. It's minus log of OH formula, OH molarity. Okay, so then pOH would be minus log of 2.5 times 10 to the minus 11. Okay, when you do that, you get a pOH value of 10.6. Therefore, my pH, because I know pH plus pOH equals to 14, would be 14.00 minus 10.6, and you get your answer as 3.4. So let me go ahead and keep 2 decimal here. So that's one way to do it. Another way, you have to remember that H plus hydronium ion, or H plus times OH minus, equals 1 times 10 to the minus 14. If you know what the concentration of hydroxide is, plug that number in here on the bottom, and then you get 1 times 10 to the minus 14, which is the product of these two, divided by 2.5 10 to the minus 11. You get hydrogen ion concentration as 4.0 times 10 to the minus 4. And then pH is minus log 4.0 10 to the minus 4. You get 3.4. Same answer as what I showed you in red. So again, in general, acid plus base equals to salt plus water. So an example is hydrochloric acid plus sodium hydroxide. You get table salt, NaCl, sodium chloride plus water. So when you have this here, if you want to write the complete ion equation, you split everybody into ionic form, and then you have water as your compound, and you have NaCl as your double displacement product, but this is a salt that's still soluble. So as you can see here, complete ionic equation has everybody in ionic form except for the water at the end and the product as liquid. So this is a complete ionic equation. Everybody is included. All of them that are soluble are shown as ions. Now, when you remove the green ones here, these are called spectator ions because they didn't change from the reactant to the product side. If you remove these guys, Na and Cl, you get H plus OH equals to H2O, which is the net ionic equation for all neutralization reactions. So let's talk about titration now. Titration is an experiment where the volume of one reagent, the titrant, is in the burette. We find out what volume of the titrant from the burette is required to react with a measured amount of another reagent that's in the flask. So titrations allow the amount of acid and base present in the sample to be determined. So you can find out molarity, moles, amount, how much of it. Indicators are used in the titration to signify the end point of titration, the point when enough titrant is added to react with the acid base present. So indicator is where basically you reach an end point where the color change will happen where you want it to end. So in this case, we're using an indicator called phenolphthalein. At the end point, it's very light pink, and if you go past the end point, you will get into a hot pink, and you don't want to get to this part. That means you went too far. And when you want the perfect titration here, you want just a little hint of pink. And that will be the end point using phenolphthalein for your reaction here. Now, we talked about titrants in burettes. So burettes hold the titrants, and then you slowly drop the titrants into the reactant in the flask here. So that's why you call it a titration. And you put the indicator into the flask here, so as you drop more stuff in, whenever it turns light pink, that's when you know you reach your endpoint. Let's try some titration calculations. If you have 22.59 mils of 0.1096 molarity HCl and it's used to titrate with 25 mils of NaOH, what's the molarity of the base, which is NaOH? Okay, so let's write the equation down. As HCl and NaOH makes NaCl plus water. So it's 1 to 1 to 1 to 1 ratio, which is really nice when we use our stoichiometry. So we know 22.59 mils of 0.1096 molarity hydrochloric acid. This can give me moles of acid here. And then I know that 1 mole of acid equals to 1 mole of base, so it's 1 to 1 ratio. Then I find the moles of base, and I can use it to divide by the volume of sodium hydroxide in liters to get molarity of my base. So that's how we would do it. We start with 22.59 mils of hydrochloric acid, and we know the molarity is 0.1096 moles per 1 liter or 1,000 mils. So you cross off the mils here. You have your answer in moles of HCl, and you know the moles of HCl to moles of NaOH is 1 to 1 ratio. Then you can cross off the moles of HCl. You get your answer in moles of sodium hydroxide. Now, you take the moles of sodium hydroxide, you divide it by the liters of the solution for the base here, which is 25 mils divided by 1,000, so you get 0.02500 liter, and you get a molarity of 0.09903 molarity NaOH. So here's another example. What is the molarity of NaOH solution if 21.93 mils of base NaOH is required to titrate with 0.243 grams of oxalic acid? So from the grams of oxalic acid, you should be able to get the moles of oxalic acid if you have the molar mass. And we also know the reaction, oxalic acid plus sodium hydroxide, you get sodium oxalate and water. So if you balance the reaction, you get a 1 to 2 ratio here. Okay, so we know that you have certain amount grams of oxalic acid. We will use molar mass to turn to moles. Once you get the moles of oxalic acid, 1 to 2 moles ratio, you can get moles of sodium hydroxide, and then you divide by the volume of sodium hydroxide in liters. That will give you molarity of sodium hydroxide. So let's go ahead and do that. Grams of oxalic acid, and then molar mass of oxalic acid. 1 mole is 290.04 grams, and you cross off grams here. You have your answer in moles of oxalic acid, and you know that 1 mole of oxalic acid will react with 2 moles of sodium hydroxide, so you get a certain amount of moles of sodium hydroxide. Then you take that number and you divide by the volume in liters, which is 21.93 mils divided by 1,000, so you get 0.02193 liters. And you get your answer as 0.246 molarity sodium hydroxide. So here's another practice. What is the concentration of nitric acid solution if 10 ml of the nitric acid solution is neutralized by 3.6 mils of 0.2 molarity sodium hydroxide? So the first thing you need is the reaction between nitric acid and sodium hydroxide. You get H and OH to get water, Na and NO3 to get your salt. So if you want to balance it, you'll need 2 waters here. So you need to find the concentration of nitric acid. But you know exactly how much sodium hydroxide you use. You use 3.6 mils and it's 0.2 molarity. So from these two values here, you should be able to find the moles of sodium hydroxide. The mole to mole ratio of sodium hydroxide to nitric acid is the same, 1:1. And then you take the moles of sodium nitric acid and divide it by the volume, which is 10 mils divided by 1,000 to get liters. So what you have here is we'll go ahead and find the moles first. So 3.6 mils of sodium hydroxide is 2.2 moles in 1,000 mils because it's 1 liter. You cancel off the mils of sodium hydroxide, you get moles left over on the top. And the mole to mole ratio is 1:1, so you cancel off the moles of NaOH. Now you have your answer in moles of nitric acid. Once you get the moles of nitric acid here, you want to go ahead and divide that by 0.01 liters because that's 10 mils, and you get your answer as 0.072 molarity of nitric acid. So some rules for writing that ionic equation. Strong electrolytes are written as a corresponding ion, so just split them up completely. And then weak electrolytes are written as molecules. So if you have, like in this case, CH3OH, CH3COOH, these guys, the OH, remember, they're not bases because they're not paired with the cation instead of just carbon and hydrogen here. So these are written as molecules. Now, solids and gases are also written in their molecular forms. Net-ionic equation does not include spectator ions, so you must always remove your spectator ions before you write the net-ionic equation. And then you must also make sure you balance the atoms and charges. So let's try an example. So write the net-ionic equation for the following reaction. You have BaCl2 and Na2SO4. So Ba will crisscross go to SO4, Na will go to Cl. So you have NaCl and you have BaSO4. To balance it, you must make sure you balance it and you end up with 2 by the NaCl. So if you wanted to write the complete ionic equation, remember you split everybody up that's aqueous into ion form, except for the solids, liquids, gases. Those guys are all written as a compound. So BaSO4 is written as a compound here. Everybody else is in ionic form. Okay? And then you see that Ba and SO4 forms barium sulfate here, so you keep that as a compound. So sodium and chloride are your spectator ions. You must remove them. Once you remove them, you have the net ionic equation. So it's barium ion plus sulfate ion equals to barium sulfate solid. Let's try one more example. Write the net ionic equation for the following reaction. So you have sodium carbonate and hydrochloric acid. You get carbon dioxide, a salt, and water. So this Na and Cl is where you get NaCl, and then carbonate will give you CO2, and then the O here will pair with the H to make water. So the total ionic equation, once you balance the chemical equation up here, Just write everybody that's aqueous in ionic form except for the gas and the liquid, okay? Or the solids too, but in this case we don't have a solid. So sodium ion, there's 2, carbonate ion, there's 1, hydrogen ion, there's 2 chloride ions, and then we have 2 Na ions, 2 Cl ions, and then we have carbon dioxide and water written as compounds. Okay, so my spectator ions again are Na and Cl, so let's cross those guys out, and all you have left when you remove the spectator ion will be the net ion equation, which in this case is H plus 2 of them plus carbonate ion equals to carbon dioxide plus water. So what is the net ion equation when hydrobromic acid reacts with potassium hydroxide? So one cool thing about is if you have an acid and a base, this is a base because it's potassium hydroxide, you will have H plus OH equals to H2O always as your net ionic equation. Acid-base neutralization, net ionic equation is always H plus OH equals to water. So we know our answer will be that, but let's go ahead and take a look at the equations here. HBr plus KOH equals to KBr plus water because K and Br will pair up, H and OH will pair up to water. And it's balanced here 1-to-1 ratio for everybody, so that's easy. And then you write everybody else in ion form except for this guy, that's water and compound. So you notice H plus OH equals to water, and then your K and Br ions here are spectator ions. Remove those guys, and you will have just your net ionic equation of H plus and OH minus equals to water. This is the end of our chapter.